Hello everyone, and welcome to this IDUG North America presentation on bringing AI into the database with Db2's Python UDFs and built-in machine learning stored procedures. And don't worry at all if you're not that familiar with the concepts of machine learning, as I'm going to give you a brief intro on it. And there are things that you'll learn about that can be used in non-machine learning use cases as well, like the Python UDF support, which can be used for any functional purpose. So even if you're not actively involved in any machine learning projects, you'll still learn about some useful capabilities here. Or maybe you can help advocate to get DB2 included as part of those ML projects. For those that don't know me, my name is Kelly Schlam, and I've been working with DB2 for IDUG for over 26 years, including quite a few years in DB2 development. But I currently work in our Technology Enablement Group with a focus on data, AI, and cloud on IBM systems. It's unfortunate that we can't be doing this in person, but it's great that we're still able to get together virtually to talk DB2. So let's get started. Here are the topics that we're going to be covering in today's session. I know that machine learning might be a relatively new area for some of you. Most of you are data experts, but haven't necessarily been involved in any AI initiatives at your company. But don't worry. As I said, I'll get you started with a quick introduction, and by the time we're done, I'm hoping you'll walk away with a better understanding of it. And I've got sample code and videos at the end to help you if you want to see or do more. Of course, like you, or like most of you, I'm not a data scientist, not even close. So anything I've learned is from self-learning and just trying things out. And that's the case with everything in this presentation. Some of this stuff isn't fully documented, and it was a lot of trial and error, and hopefully I can help you with this get started faster. In terms of the deck, I've also tried to add additional information to all of the speaker notes, so you can download the deck and give it a further read. The bulk of the material here is going to cover the new built-in machine learning stored procedures, as well as the ability to create user-defined functions written in Python, which you'll see allows another dimension to in-database machine learning with DB2. So with that, let's begin. I know you've all heard the term artificial intelligence before, but there are a few other terms I want to quickly cover just to ensure we're all on the same page. Because although you may have heard them before, you might not understand their meaning exactly, or you may actually hear people use them interchangeably, which isn't actually correct. AI. This is a pretty broad term, meaning any system that mimics human intelligence in some way. It could be a computer chess player, or a self-driving car, a factory robot, or even an automated email spam filter. Machine learning. It's a subset or a subfield of AI, so that's why I'm showing it within AI here. And machine learning is the development and use of algorithms and models that learn from data without explicitly programming it to be able to make predictions. And by that I mean being able to identify something or prescribe an action to take. And deep learning is a subfield of machine learning, where you're performing complex tasks like image classification or object detection or natural language processing. And the reason it's called deep learning is that they utilize neural networks to process the vast amounts of data presented to them. And it's deep learning because these neural networks typically have a number of layers to them. They're deep. And finally, data science. This is one of those terms you might hear somebody use interchangeably with AI or machine learning. And truthfully, I might even do that myself at some point today. But data science isn't just the algorithms or the technology. It's the overall process and practice of hypothesizing and experimenting and evaluating results and putting them into action, using different approaches and technologies. In other words, you can kind of think of data science as being the scientific method and putting the findings into practice. And AI and machine learning are tools at the data scientist's disposal. When I started reading up on machine learning a few years ago, I found it difficult to define what a model is exactly. I saw the term used everywhere, and obviously I have my own notion of what a model is, but I never really found a consistent definition of it. Articles kind of just assumed you already understood the concept. Or even deeper than that, where do these models or algorithms come from? Who writes them? Does building a model and training a model mean the same thing? For the purposes of this presentation, let's just say that a model is an algorithm, a mathematical formula or representation that can be used to make predictions. And again, by predictions, I mean to identify something based on its characteristics or to prescribe an action to take based on the data at hand. There are a number of different algorithms or models that have been developed, some more applicable than others to certain types of problems or domains. And data, sometimes very large quantities of data, are fed into these algorithms to fit them to that data. And the process of learning from the data is called training. Think of a really simple example where some relationship of an input variable to an output variable is a straight line. This is an example of linear regression. For example, there's a type of cricket whose frequency of chirping varies according to the temperature. Or maybe you could correlate the number of hours a child spent studying for a test with the final mark that they get on it. So think back to math class and the slope function, y equals mx plus b. And in machine learning, you'd feed a whole bunch of past student study times in that last example I gave you, along with the final grades that they got. And the training process would look at that data and it would adjust the line, its slope, the y-intercept, and so on, until it found a line that best fit the data. So that's the process of training the model. And here, this model could then be used to predict grades for future students, again, based on their study time. Of course, real-world problems are much more complex than this, and they might deal with tens or hundreds or even thousands of input variables, some of which are irrelevant, or some are more important to the result than others. But hopefully this simple scenario helps you wrap your head around this concept a little bit better. So here's a really simple scenario, a banking use case where they want to be able to identify whether a customer is going to default on their loan or not. They've got their historic data of when people have defaulted before, and this is exactly the kind of transactional data and historical data that people keep in DB2. And based on that and what they know about the customer, maybe their age, income, and whether or not they made their last payment on time, can they correlate that information with whether or not a customer is likely to default? And that's what machine learning is, finding the pattern, finding how you can determine a dependent output variable, the default column here, based on all of the various input variables available, some of which may be relevant, some not, and some more relevant than others. But in real life, there's likely tens or hundreds or maybe even thousands of input variables to be considered. And that's what makes machine learning difficult and time-consuming, and what DB2 is helping to support. Just to give you a bit more basic machine learning knowledge, here are some of the common machine learning techniques you might see when getting started. Regression and classification are two common techniques for supervised learning, which is a class of problems in machine learning where a model is trained to learn a mapping between input variables and a target output variable. It's called supervised learning because the training data includes the result you're trying to predict, like the past student scores in the example I just mentioned, or the frequency of the cricket's chirp, or whether or not a customer defaulted on their loan in the past. The input data is labeled, and the algorithm is explicitly told what it's trying to solve. Not how it's trying to solve it, but what it's trying to solve. Regression and classification are the two primary types of supervised learning. Regression problems are like when you want to predict future sales, or given past home sales. Can you predict what a house will sell for based on the number of bedrooms, bathrooms, yard size, and so on? Classification is about categorizing the data. Is this client a credit risk? Yes or no? Or is this a picture of a cat or dog? Or as you'll see in my example later, what species of flower is it, based on its measurements? Unsupervised learning, on the other hand, deals with unlabeled data. There is no target variable or expected outcome. Instead, it's about finding patterns and relationships within the unlabeled data. Clustering is an example of this, where you want to segment and group the data. And this is often done for things like targeted advertising or creating recommendation engines. I don't include anywhere in here one of those standard slides on examples of where machine learning can be applied, because frankly it applies everywhere, to every industry and business domain. And if you're unsure how it's being used or could be used in your own industry, simply Google machine learning and your industry name, and I'm sure you'll be inundated with results. This is the typical machine learning workflow. A rather simplified view of it in practice, but it captures the main points, like data ingestion and transformation, training of a model based on that data, and then using that model for predictions against new data that comes in. In practice, though, there are loops and repetitive processes in here. It's not exactly the straight line that's shown. And data scientists spend a ton of effort at different points here. For example, data is rarely perfect, so they need to worry about how to handle missing values or obvious outliers. Do you keep these data points, replace them, or alter them in some way? They're likely to try out different algorithms and model types. They're going to adjust parameters and make slight variations, and they're going to run their training and tests over and over and over again. And another key piece, and this is where the experience of a data scientist comes in, or the benefit of an auto AI platform, is a process called feature engineering, which is where they might transform some of the columns from one form to another, or combine them in some way. Let's say you're building a model for a retail outlet that's forecasting sales for each day next week. You'd be using past sales data as input, and in there you've likely got a date column. But a date on its own, let's say, June 18th, does that really mean anything on its own? So maybe instead of using the date as is, you take that date column and you make another column out of it. Perhaps a Boolean, is this day a weekend, or is the day a holiday column, which is going to be much more useful to a machine learning model than a date itself, and will have more of an impact on determining how sales are predicted than that base date. And so the data scientist does all of this in a very iterative and repetitive fashion, trying things out and repeating tests over and over again, maybe with slight variations, evaluating all the models and determining what performs best. And even when they're happy with the model they have, maybe its accuracy diminishes over time and needs retraining, so you loop right back to the start. But at a high level, what's shown here are the general steps involved. Also, I've used the word predict a few times already, but you may also hear this referred to as inferencing or scoring, and I'll very likely use a mix of these terms throughout the presentation. So with the new capabilities in DB2, where do they fit into this workflow? DB2 now includes a number of stored procedures for doing in-database machine learning. And this includes other form factors like Db2 Warehouse and Db2 Warehouse on Cloud, where these procedures actually came first. Anyway, you can use them to build regression, classification, and clustering models within the database, and then use the resulting models to score other data in the database. And in addition to those, DB2 now supports UDFs that are written in Python, which lets you do things like bringing externally developed models into a UDF to do in-database inferencing. And it's these things that I'm going to be covering throughout the remainder of this presentation. And just to be clear here, the Python UDF support isn't limited to machine learning use cases. You can implement any business logic in there that you want, just as you can with UDFs written in other languages today. But there's a lot of opportunity here around in-database machine learning, and so that's what we're going to be talking about today. A big question you might already be asking is, what exactly is the benefit of doing machine learning in the database? I mean, if there are already well-defined platforms and approaches to building models and using those models, why do any of this in DB2? Now, this really isn't that different compared to other things that have been added into DB2 over the years, like the built-in BI and analytics capabilities. You've got your data in DB2 already, so if you can do the processing where the data lives, versus having to copy and moving data elsewhere to the processing, there are a lot of positives that come from it. So as you're aware, data is at the heart of machine learning initiatives. You can't build accurate and useful models with bad data, or with data that you can't trust. And you, and I do mean you, the data professionals, the database administrators, those listening to this, you've already made the effort to clean your data in the database, to secure it and govern it. So why not take advantage of that? Being able to train models in the database means no data movement. So you're avoiding issues of governance and security. You know you're dealing with the most recent and fresh data. And just generally speaking, it's a less complex process with potentially less systems to maintain. Now, even if your organization decides that you need to do your model development work elsewhere, for whatever reason that is, you've still got the ability to deploy the model within a Db2 Python UDF for real-time in-database inferencing. So let's talk now a little bit around the specific benefits to each of those two different approaches, the built-in stored procedures and the Python UDF support. The new stored procedures offer a number of different model or algorithm types, which you'll see on one of the next charts. But the point is that they're built in. You don't need to write code to train the models. You just point the procedure at your input data, and it does the training. Another benefit of doing your training in DB2 is that you don't need to be moving your data out of the database to your training platform. And you might be talking about very large quantities of data here, so that's a key benefit. And DB2 can also exploit multi-node processing and DPF to train your models faster. Now a few of the benefits of the Python UDFs. So it could be the case that you have a data science team that is developing their models by hand using Python code, or in a notebook, again probably using Python, or maybe using an automated AI platform. In which case you could take those models and run them inside of a Db2 UDF. I've got a couple of diagrams here showing different options for doing that. The first is a case of importing a model into a Db2 Python UDF and performing inference processing directly inside of Db2. And I'll cover this approach later. The second one represents the case where the model remains hosted outside of Db2, but the UDF is written to make REST API calls to the model. And you can call the UDF to perform an inference operation, but the inference processing itself is being done elsewhere. And I've got a slide on that later as well. These are the different types and categories of stored procedures currently available in Db2. And there are ones for evaluating your data, some basic transformations like replacing missing data or splitting data into training and test data sets. You can train decision tree models and linear regression, naive Bayes, and k-means models, and then perform inferencing using them. And you can evaluate the performance or the accuracy of your models based on data not seen during training. So you're holding out a test data set and you're evaluating that. And lots of different things included here that you can do as well. So rather than just spewing syntax diagrams, I thought it would be more compelling to go through a simple use case, highlighting a number of the different procedures. Not all of them, but a good portion of them. You probably weren't expecting flowers, right? I could have used a more business-like scenario for this, but anything of interest would have been that much more complex, and possibly a bit boring. And in truth, I find this really useful as a simple machine learning scenario, as it's a small data set and it's not that hard to wrap your head around it. And because of that, it's actually used a lot in machine learning education. So some of you may have already seen this scenario before. Basically, you've got these three species of iris flowers: Setosa, Versicolor, and Virginica. And now that I'm saying them out loud, I'm not even sure if I'm pronouncing them correctly, but hopefully I am. And then there are four measurements: sepal length, sepal width, petal length, and petal width. And based on these measurements, you can predict the species. Here's what the dataset looks like. Each row represents a data point, a measurement that was done in the field, with the four individual measurements I just mentioned. The last column here is the species, and because we're providing the target column, what we want the model to predict in this case, this is a supervised learning case. And because we're trying to predict which class or label to assign, it's a classification problem. The dataset itself only has 150 rows, 50 of each species. I've got a link to a CSV file here if you'd like to try this out yourself, but if you Google it, you'll find it in a lot of different places. For example, it's available on Kaggle, which is a data science community. Before you can use the stored procedures, they need to be set up, and these are the steps that you would take when creating a new database. You can also enable them in an existing database using the upd v11.5 command, which I describe in the speaker notes. On this slide and others, I try to highlight some of the main things to note, like I've got with the arrows here. I won't read them all out, but hopefully they're useful as a reference. One important thing to mention is that these stored procedures are only supported on Linux, on x86 and Power, and on Linux on Z as well, but not all of them are available there at this point. Again, further details are in the speaker notes if you're interested. The first step is to import the data, although in practice you'd likely have a good portion of your data in the database already. It would be your business data, your data of record. The procedures depend on the input data having a unique identifier column. So if your data doesn't have one, you can create an identity column, like I did here. Many datasets you download from the internet include a header with the column names. And if you use the import command, you can tell DB2 to skip that row with the skip count option. In practice, you may have to manipulate your data somewhat to get it in a form ready for machine learning. Like, how do you handle empty or null values? And for numbers, would you use 0 for a missing value, or the average value of all the other rows? These are the kinds of things that data scientists think about. This Summary 1000 procedure gives you some insight into your data, calculating stats for up to 1,000 columns in the input table. Again, the data scientist likes to understand their data and make sure it's clean and is in good shape for training. So that's where this comes in. You must provide the input table name and the output table where you want the summary information to go into. And that's it. DB2 will actually create multiple tables, as shown here, depending on the type of data in the table, and with the output table name as the stem of these other tables. Examples of the data collected is shown in the left white box here. I didn't include it here, but there's another useful stored procedure called column properties, which will give you just that, the properties of the different columns in your dataset, which is just another thing you can use to better understand the data. In addition to ensuring you've got high quality and trustworthy data, it may also be necessary to massage the data and get it into a form that's more consumable by machine learning algorithms. For example, if you're dealing with numeric data, and different columns have different scale and distribution characteristics, maybe there's a need to standardize or normalize the data. And there's a procedure called standard norm that can do that for you. Another common task that data scientists do is called data imputation, which is essentially filling in missing data in your data set. Now, if you've got some rows with one or more missing column values, maybe you just delete them. If it's a relatively small and random sampling of data that's incomplete, that might be an okay approach to take. And the data scientist may do that, but then they may also impute the data, substituting values for the missing ones, and see if this results in a better model. To be clear, in the context of DB2 and these stored procedures, missing means null values. A value of 0 for a numeric column is not a missing value, nor is an empty string. Those could actually have valid meanings, like 0 being the number of children somebody has, or the number of defects identified in something. So the question then is, what do you actually replace these values with? And DB2 offers 4 different methods for substituting the missing values. For numeric columns, you can have DB2 replace nulls with the mean or median of the rest of the values in a column. Or you can have DB2 replace them with the most frequently occurring value. And this can be done for both numeric and non-numeric data. Or you can explicitly specify what value you want used for all of the nulls in the column, if there's a default that makes sense. Now in practice, you may have to actually perform this step multiple times for each column in the table. For example, just looking at the iris dataset here, it's probably not a good idea to fill in a missing petal width value for a setosa flower with an average of all petal widths for all flower types. That might actually impact the usefulness of the data overall. Instead, you'd probably want to use the average for only the setosa flowers in the input data set. Now, the stored procedure doesn't know the target column that you're trying to predict here, so it can't determine what rows to look at and which ones to skip when calculating those means or median values. So that's up to you to do. And you can do that, for instance, by creating a table to put just the setosa rows into. Or you can also create a view on top of that iris table that just contains those rows. And so that means you'd probably have to do this then for all of the measurement columns for each flower type to, effectively fill in these missing values, with something that's useful. Here are just a few examples of the procedure, showing all 4 of the different methods. I've also highlighted the different options you can specify, like how you specify the input table and the output table, or how you can be specific about which column or columns you want it to transform, since by default it does all columns in the table. And if you want to use an explicit value, you can do that as shown here for a numeric value, but you can also specify a string if you want to for a nominal column type. And just to be clear, if you download this iris data set from anywhere, it's not going to have any missing values. This is just shown here for example purposes. So which one of these methods is better? It probably depends on the data and what kind of problem you're working on. Again, this is the kind of thing where the data scientists may actually try them all out to see if one method generates a better model than the others. When building a model, you generally use both a training dataset and a test dataset. The training dataset is used for just that, training the model. The test dataset, on the other hand, is held back from training and is used to evaluate how well the model performs with data it hasn't seen before. Keeping in mind that it's still labeled data, and so you can compare the predicted value with the actual value for each row in it, and calculate some metrics around it. Sometimes you have this data split out already, but if not, then you can use this split data procedure. And you can specify what percentage of the data goes to training and what goes to the test table. So a general rule of thumb is that you use about 80 to 85% for training and the rest for test. So here you provide the input table and the two output tables, train table and test table. Now here's where the magic happens. We're going to build or train our model here. You'll remember that DB2 includes a number of different algorithms, and this use case is a classification use case, since we're trying to identify which of the three species a flower is. And because it's a classification problem, we can create a decision tree, which is a type of classification model in DB2. A benefit of decision trees is that they're explainable. They're like flowcharts that you can follow through to the final decision in classification, like I'm showing here with the tree on the right. Many models are complex black boxes, and it's difficult, if not impossible, to understand the logic employed behind them. And that's particularly problematic in certain industries or countries where you have regulatory requirements around AI, and you need to be able to explain the results. So decision trees are useful at understanding the results. The grow deck tree procedure will build out a decision tree model based on the input data you give it. And you can use the print model procedure to display information about the model. And in the case of a decision tree, it's a visual representation of it. Now, DB2 externalizes some of the training parameters, what are called hyperparameters, and you can adjust them to build different models and compare their accuracy to help choose a final one. Now that we've got our trained model, we can use it to make predictions. And as I said earlier, this process is also commonly referred to as inferencing or scoring. Now, you don't score a row one at a time by calling the procedure. Instead, the data to be scored is provided via a table. And you specify that input table in the command, along with the output table where the results will go. And this table will be created if it doesn't already exist, so you don't need to create it in advance. For each row scored, you get the identifier of the row, so you can link back to the original input table, the predicted class, the species name in our case, and optionally, the probability of the prediction. For example, a result for row 4 might be that it's predicted to be Virginica with a likelihood of 95%. Now, if you want to know the probability for each class for every row, not just the predicted value, you can specify an outtable prob table. So the probabilities for row 4 might be Virginica at 95%, Setosa at 3%, and Versicolor at 2%. So now you've got your model, but how do you know how accurate it is? A common tool of the data scientist is the confusion matrix. It's a visual representation of correct and incorrect predictions, based on running the model against the held back test data, where you know the actual class and you have the class that the model predicted. Ideally, what you want to see is big numbers down the diagonal, so correct predictions, and small numbers outside of it, the incorrect predictions. The confusion matrix procedure will generate a table of real versus predicted values from which you can calculate true positives, true negatives, and false negatives. And data scientists use these numbers to calculate metrics like accuracy, recall, precision, and F1 scores, each having its own place for determining the predictive performance of the model. But we won't go that deep here. If you run into errors while calling the different procedures, you might get something helpful, a useful error message, but you might also get a general error with an embedded error code in the form of CDFAA followed by a number, along with message text that's quite likely to be truncated. But you can get the identifier and the full message text through the last message code and last message variables. And once you're done all this, you need to clean up. You can drop any models you don't want to keep along with the summary table if you don't want to keep that either. And the other tables that were created along the way, like the prediction results or the probabilities table, you'll need to clean those up manually with the drop table statement. Let's now take a look at the new Python UDF support in DB2. This is supported in DB2 11.5.5, but it's not actually documented in the Knowledge Center, but it is in the DB2 warehouse documentation. I couldn't find anything that explicitly states where it's supported, but I successfully tested on both Linux on x86 and Linux on Power. I tried it on AIX and doesn't work there, but I didn't have an opportunity to try it on Linux on Z. With respect to the Python version, I could only get it to work with Python 3.6 and higher. I think I tried 3.6 and 3.8 and 3.9. 2.7 is no longer being maintained anyways. It's past its end of life and you shouldn't be using it. And actually on that topic, Python 3.6's end of life is later this year, so best to use something more recent than that. You can create scalar functions in Python, which is what I'm going to show over the next few slides, and you can also create table functions and aggregate functions. The only DB2 setup you need to do is to point the dbm config parm to your Python executable, to Python 3, or just Python if it links to Python 3, wherever that's installed on your system. Python UDFs have to run as fenced, which means that the fenced user ID, which could also be the instance ID if your instance is configured that way, but in any case, the fenced ID has to have access to this Python 3 executable. Let's start with a really simple example, a function that adds two integers together and returns the result. Here's the source code for it. Every Python function must import the nzae or nzae module and have a class derived from the nzae.ae class. The main code is driven from the getFunctionResult method, and it's initiated by the run method against the class, as shown at the bottom. The input parameters are passed as a list into it, and you can pull the individual parameters out of it as needed. Of course, something more involved would need the appropriate error handling and such, like making sure the input data is valid and not null. But actually for nulls, you can define the function to not be called when the input is null, and the caller will automatically get a null result in that case. And here's the command to create the function, with that returns null on null option that I mentioned there. And there are a few other things to note, like the language needs to be set to Python. The parameter style is NPS generic. The UDF has to be defined as fenced. And you need to point to the location of the source file, which needs to be somewhere accessible by the fenced ID. And when somebody makes a call to the UDF, the fence process loads the Python bootstrap script, runpy.shell, which is located in the sqllib/adm directory, which then loads and runs your file. So not really important for you to know it all, just a little bit of info in case you like poking around on the system. When you end up with examples in presentations like I'm showing here or what you're going to see in other people's presentations, that's usually the result of a lot of trial and error and working through problems that you hit. And so I thought I'd share some of my pain with you so you can avoid them or easily identify them if you run into them in the future yourself. Like if you accidentally set Python path incorrectly, or the executable isn't accessible to the fenced ID, then you're going to get this kind of cryptic error you see at the top. And if you specify an invalid source code path, one that doesn't exist, as part of the create function statement, you get this second error talking about the file not found, but the message itself doesn't say which file. And if the file exists but isn't accessible, then you get this permission error. And the most common case I ran into was a programming error in my code. Some sort of syntax error or accessing a variable incorrectly, things like that. And in those cases, you get this nice generic error message, but it does include a snippet of the actual error returned by the Python code, as if you were running the Python code on the command line. But sometimes there isn't enough of that message to actually be helpful, in which case you need to do or look at other things, like the routine log or add additional debug code, and I'll cover that next. Let's talk a little bit about debugging. The DB2 developers have made it easy to log information from your Python UDF to a log file, which is really helpful for debugging your programs. The notification log is found in the diag path in a directory called routine log. And when errors are encountered, information sometimes gets dumped to this file automatically. Like if you get an exception, then a stack traceback gets written there. But also, you can write your own messages to it. The self.log function accepts a string, and that string gets printed out to the notification log. And the cool thing about Python is that you can pretty much turn anything into a string just by using the string function. You can easily convert an array or a list or an object to a string, and you can also concatenate strings together with the plus sign. So I was creating rather complex output messages with formatted two-dimensional arrays and lists and objects and texts, which really helped me a lot as I was working through all of this stuff. And here are some final hints and tips, some of which is just a summary of the things I talked about, but a few other things as well. I mentioned ensuring that the config parm is set correctly, and that means pointing to a Python 3 executable, which needs to be accessible to the fenced ID, either the instance owner if they're the same or the separate fenced ID. I did do some limited testing of a virtual environment, and I don't mean a VM, but the virtual env command or the venv module of Python, which lets you set up an isolated Python environment or a bunch of them together on the same server, and they can be used by a single user independently. And this did work for me. If you're doing this on DPF, then the Python source file needs to be in the same location on each server. Likewise for PureScale. Although I didn't actually test PureScale, but I saw something somewhere, can't remember where exactly, that did suggest it is supported there. Again, the script obviously has to be accessible. And then as I was talking about on the last slide, from a debugging perspective, you can use the routine log that I just talked about. Also, for some of the more complex stuff I was trying, rather than just jumping right in with DB2, I found it easier to create a standalone application first that did what I needed. Then I made changes to it to make it a UDF, wrapping it with that code I showed you earlier. So that was all just the basics on Python UDFs. So let's take it in the direction of machine learning now, and specifically using models developed elsewhere and running them inside of a UDF. Now, you may have been able to do this before with Java and C UDFs, depending on how and where the model was built and the runtime code generated for it. But Python is the de facto language of machine learning, and most development work and the code to deploy and run these models is in Python. So that's what makes this a good fit for the Python UDF support in DB2. I should say that what I cover over the next few slides is based on my own testing. None of this is in the documentation. And so there's a lot of trial and error and piecing together of the limited information I could find, and had some help with a few of the lab folks. So I can't necessarily say that what I've done here is the best way to do something, just that it worked for me. But I do hope and expect that you'll see a lot more info around this topic in the documentation going forward. In my own testing, I tried a few different scenarios, like building a model using scikit-learn, which is a very commonly used open source machine learning framework. Did that in a Jupyter Notebook. I also built models on a couple of automated AI platforms, in particular Auto AI in IBM Watson Studio and H2O driverless AI. And all three of these scenarios used a different approach to exporting, loading, and running the models. So I don't cover all three of them here, just the scikit-learn example. But I do have a couple of YouTube videos I created showing the others, and I've got links to them at the end of the presentation. And one really interesting thing about my testing was that I was able to develop models on Linux on x86, and then I was able to run them with DB2 running on both Linux on x86 and Linux on Power. And that's little endian Linux on Power. So data scientists may do their development work on x86, but you can then deploy them to enterprise DB2 systems running on Power. It's certainly possible, though, that some model representations might not work cross-platform like that. I don't know. I can only talk to what I tested. And with these three different scenarios, I was able to do this kind of cross-platform development and deploy. Now, with respect to AIX specifically, I mentioned earlier that the Python UDFs don't seem to be supported on AIX. But you could have your own standalone inferencing application running on AIX on Power, doing inferencing close to where the data lives, if that's where your databases are. I mentioned scikit-learn on the last slide, so here's just a little bit more about what I did there. As I said, it's a free open source machine learning library for Python, which includes a lot of different algorithms and model types, which could be used for classification, regression, and clustering use cases, among other things. And the IRIS dataset I talked about earlier, it's actually a commonly enough used educational dataset that it's built into scikit-learn. And you can load it with just a single function call, which I'll show on the next slide. And it already knows what the input columns are and what the output column is. And if you want to take a closer look at this notebook or try it yourself, I've included a link to my GitHub repository here, and I've got a lot of other samples there as well. So here's the code I wrote to load the data and display it. The first line does the load. Then you can view the feature names. And I can't remember if I mentioned features and feature name before, but essentially that's just the input variables, the input columns. Remember I talked about feature engineering? That's where the data scientist may transform or combine or do stuff with the data to get it ready for machine learning, to get it ready for training. Those are referred to as the features. So the four features here are those input measurements: sepal length, sepal width, petal length, and petal width. And it already knows what the target column is, and it knows what the three target classes of that column is, the three species. And then here I'm printing out the first few rows of the features, the input columns again. This is the portion of the notebook where the model gets trained, where it's fitting the model to the input training data. So I'm creating an instance of a decision tree classifier model and then training it or fitting it. I just realized I don't actually split the data into training and test sets here, or evaluate the model's performance or try any test predictions, but I'll fix up my notebook at some point to do that. In any case, that's it. I've got my trained model with just a few lines of code. Now, to be clear, a real-world scenario is going to be more involved in this. I mean, there's a reason that data scientists get paid the big bucks, and that's why automated AI platforms are becoming increasingly used as well, because they're likely to have to write a lot more code than I've got here. Remember all that stuff I talked about earlier about cleaning and transforming the data and that feature engineering, again, that slicing and dicing and transforming and combining the data in ways that make it more effective for training? Oh, and I arbitrarily chose a decision tree here, but there are a number of other algorithms to consider as well. And data scientists would want to try them out and adjust parameters like, the maximum depth on the decision tree to see if they can build a more accurate model. And then they'd evaluate all the different models and look at metrics and those confusion matrices and all of that stuff. But I'm not trying to teach you data science here. And I'm obviously just not qualified to teach you data science. So my very simple model here is really good enough for our purposes. And there are different ways that you can visualize different types of models. Like with this decision tree, you can get a textual representation, as shown in the notebook screenshot on the left, as well as a flowchart style representation here, as shown on the right. So now I've got this decision tree model I want to deploy. Maybe I've got scientists in the field taking measurements and they're being entered into a DB2 database. And I want to use this model in a UDF so that people can determine the flower species for each of the data rows entered. How can I take this in-memory model running in Python and then get it into DB2? Well, first, what I can do is dump or export this model out to disk. I don't actually know what's inside this object, but it's relatively self-contained. And once instantiated, you can use it to make predictions. So Python has a lot of useful modules and cool libraries to do different things. And for example, Pickle is a process or protocol in Python that takes an object hierarchy and converts it into a byte stream. And that byte stream can then be unpickled or reverse engineered back into the object. So you can take your model object, pickle it to a byte stream, and write that byte stream out to disk. But there's actually a function that does all of that for you in a single call, and it's the dump function of the joblib package. And there's a corresponding load function as well. And so that's what I'm doing here. I'm writing a serialized version of the model out to disk, along with the target names, which are the species names, because for some reason they're not in the model object anywhere. At least I couldn't find them there. And I want my UDF to return the species name to the caller, so I need to pass along the list of the species names into the UDF as well. So that's why I'm dumping both the model and the species names. Let's jump over to DB2 now, and I've got my UDF source code up here. I've highlighted the major areas of the code, but there are a couple of things I want to point out specifically here, like where I'm loading the model and the list of target names, the species names, in from disk. Again, this is the unpickling where it's being deserialized from the on-disk byte stream back into an object. And down here is where the model is being used to make a prediction, passing in the data row passed in, massaged to get things in the right format. This model doesn't directly return the name of the class, which is the name of the species in our example. It actually returns the class ID, and there are 3 classes, so 0, 1, and 2. That's why I had to store the class names to disk and load them here, so I could then do a lookup into them based on the class number. And then ultimately I return the species name as a string to the caller. And remember, if you run into any code issues along the way, you can always write things out to the routine log to help you debug it. With our source code in place, we can now create the function. You can see I accept 4 float numbers as input. These are the sepal and petal measurements, and it returns a string. Maybe I should have used decimal values, but at the end of the day, it doesn't really matter. And to avoid having to check for nulls in the code itself, Db2 does that for me and automatically returns null if any one of the input values are null. And then here's a single call example showing what gets returned for these particular measurements. In this example, I'm simply returning the species name, but maybe you also care how confident the model is in predicting it. So you could write a partner UDF with this one that actually returns just the probability. So you could pass the same values into both functions and get the species name and the probability. Although a better approach to that would be to actually create a table function, so a user-defined table function, that returns a 1-row table that contains the class in one column and the probability in the other. Or you could have it return, for this particular example, 6 columns. You could have each one of the species along with each one of the probabilities associated with it, and then the calling application could do something based on that. So maybe I got a bit ahead of myself there, as that user-defined table approach is what I'm showing here. So rather than the scalar functions I've showed up to this point, here's a function that returns 2 values, the predicted species name and the probability associated with that prediction. As you'd expect, there are some differences in the underlying source code, the create function statement, and how you call the function, compared to what you've seen already. The code is in the white box here. And rather than showing all of it, I'm just including the important piece, which is get function result returning 2 values. You can say return variable 1, variable 2, and so on. And the blue box at the top has the create function statement, defining it as a table function with 2 output parameters, a character column and a float. Again, this could just as easily be a decimal. And then the blue box at the bottom has an example query calling the function, with a single row result from the table as a table, with the species and probability column values. Now, in addition to the scalar and table function types, you can also create aggregate functions in Python as well. In terms of how you'd use those, you've got your standard examples of calculating a sum or an average or something like that across multiple input rows. But I haven't really considered how this kind of thing might be useful for machine learning workloads. Then again, I really haven't given it that much thought though so far either. But anyways, both scalar and the user-defined table functions certainly do fit a need. As I was trying all these different things out, I was wondering how else you could take advantage of an inferencing UDF. And that got me starting to think about triggers. It occurred to me that you could automate inferencing of new data coming into the database through a trigger. So what I've got here is a table where the new data is being inserted into, so where a row with the 4 measurements are added, and then there's that species column at the end that isn't explicitly inserted with the data, because obviously they don't know, but it's filled in automatically through a trigger. I created a before trigger that calls the UDF with the 4 measurements and then inserts the species name returned from that function into the last column of the table. And so at the bottom, I've got some sample insert statements here, along with the contents of the table after the inserts have been performed. So I thought this kind of thing was a little bit cool and worth mentioning as something interesting that you could do with these UDFs. And it's quite possible that you can think of a lot more uses of these UDFs as well. I briefly mentioned Auto AI earlier, which is an automated machine learning technology found in IBM Watson Studio, which is a component of IBM Cloud Pak for Data. Remember all those steps I talked about earlier in the presentation, like data transformation, feature engineering, model selection, and evaluation? Well, all of this is automated in Auto AI. You just load your data set, tell it which column is the target column you want to predict, and that's it. So again, it does that automated feature engineering, and it tries out different algorithms, different models. It varies the hyperparameters or the configuration settings of the different algorithms as well. And all the while, it will pursue paths that look promising to it and abandon those that don't. And when it's done, you've got a ranked list of its findings, with scoring pipelines that then can be deployed and used for inferencing. And this is another way that technology advancements are helping democratize AI and open it up to a wider audience. Just like what's being done with DB2 and the built-in store procedures. Although to be clear, that isn't auto AI inside of DB2. I just mean that these capabilities are helping make machine learning easier and more widely used. And as I mentioned earlier, you can actually export these auto AI models out to disk as well and use them in a DB2 UDF. And that's a little bit more involved than the scikit-learn example I showed earlier, but it's still pretty easy. I don't want to get into all the detailed steps here, but if you are interested in seeing that in action, I've created a YouTube video and I've got a link to it at the end of my presentation here. It's quite possible that an organization has well-defined processes for how and where models get hosted, and there might be logistical or technical reasons that they don't want to copy them to a DB2 server and run them inside of DB2. In this case, you could still have this in-database inferencing using a Python UDF, where the UDF is called via SQL to make a prediction. But the inference processing itself is being done remotely, and the UDF would be making API calls to wherever the model actually lives. And that's what I'm trying to highlight here. And in practice, though, there's no reason you couldn't be doing that today with UDFs written in other languages as well. But as I said, Python has a lot of different modules and packages, and there are ones that make calling REST APIs and processing the results really easy. So it makes a lot of sense and is easy to do with the new Python UDFs in DB2. We're now at the end of the presentation, but before I finish, I'd like to quickly point out a few things for you to take a look at if you're interested. I've got a link to the in-database machine learning section of the DB2 Knowledge Center, and I've also got a couple of YouTube videos I made showing off this stuff in practice. I've also got a link to my GitHub repository where I've been putting the scripts and code that I wrote. And that includes SQL for the machine learning store procedures and some code and notebooks for the Python UDFs. Might not be the prettiest code I've written, but hopefully it's good enough to help you get started. I'm going to try to post things to GitHub more often now. I just need to figure out how to get this stuff to show up in Google searches so people can find it when they're looking. And if you want an environment to try out some of the things I've shown, Obviously, your own DB2 environment if you're at the latest and greatest levels. But in terms of writing notebooks and creating models outside of DB2, you can take a look at Watson Studio, available in IBM Cloud, as well as a free Cloud Pak for Data as a Service environment, and I've got a link to that here. Or if you've got stuff installed locally, Jupyter Notebooks, you've got Anaconda on your laptop, things of that nature, you could try that stuff out and use that as well. I hope you enjoyed this presentation and feel like you've learned something, even if you're not directly involved in any AI initiatives in your business. Hopefully it's just given you a little more awareness and make you feel a little more comfortable with the use of AI and DB2. And please don't hesitate in reaching out to me if you have questions. And in fact, if you're doing any machine learning with DB2 in any capacity today, I'd love to hear about it. And please remember to fill out the session evaluation form. Thanks, take care, and enjoy the rest of the conference.